the main idea behind this, actually I was debating, I had an internal debate whether I should talk about semigroup actions or C-spaces, and well, I decided to go with this. It's based on a joint work with Ken Davis and Adam Fuller, with the appear in Memoirs, and then there is a spin-off of this work. It's going to appear in IMRN. The main motivation behind this work is actually what we do most of the times with operator algebras. We try, starting with some geometric or topological structure, we try to associate this a bunch of operators. Operators, of course, on a Hilbert space. And we try to do this encoding by remembering as many things as we wish from the original structure. And then we can explore this encoding here by checking whether properties of the structure are translated to properties of operators and algebras that they form. And this one way of doing so, well, one other thing that we'd like to see is whether we can go back, whether isomorphism at this level can be translated into some isomorphism at this level. And these isomorphisms can be either star isomorphism, it can be Morita equivalence, or your favorite one. This work starts from one of the basic structures, and it concerns system dynamical systems. And well, dynamical systems have been around for many, many years, and we know how to make a pass from the W star context to the C star context when we have a group action on the C star algebra A. However, what we don't know, or we haven't agreed yet, is what is the analog of this construction of the C star cross product when you have just a semigroup action on the C star algebra A, which may act by star endomorphisms that are not invertible. And my plan is to explore a little bit the operator algebras that arise in this context, and show you how you can link them to what you already know, and use this plan, this scanning plan, to get some information, to get new theorems for semigroup actions when you already know things for automorphisms. The case example, in any case, it's Z plus. So to give a motivation, system dynamical system over Z plus is nothing else but a single star endomorphism of a C star algebra. And the way that you would like to encode it is to check what happens to the orbits of elements. So you want to use operators to encode what happens to an orbit of a single element, where the only thing that you can do is taking powers of alpha. The key idea that applies also to the C star cross product construction is to introduce an external operator V that satisfies the following covariance relation. When A meets V, then it transforms into alpha phi. That's the basic idea. V is something like a wall at discrete time, and when the element passes through that wall, then it changes. Most of the times, well, if you like to reverse time, you would like also V to be an isometry. So if you know what happens at equals 2, then sometimes you know what happened at equals 1 and equals 0. So most of the times we take V to be an isometry. However, when you have an automorphism, then you can take also negative powers. Perhaps you would like to encode this data. You would like to include this data in the operator algebra that you construct. And therefore, instead of having just a V to be an isometry, you would like to be a unitary. And this brings us to a nice example of such a pair of a representation of A and a unitary U. When A acts on Hilbert space H, you take the L square of H, and there you take the bilateral shift, the forward bilateral shift, backward. And for the representation of A, you take the diagonal along its orbit. And it's easy to check that it satisfies U and by satisfies this covariance relation. Since U is a unitary, it also has one more property. It undoes alpha, or equivalently, it implements alpha. But I like to set my notation for later, so this is why I write it in this horrible way, instead of saying that it implements alpha. The Gibbs-Varian uniqueness theorem tells you that the sister algebra generated by pi and u has a nice property. Every other pair that meets the gauge action and also pi prime is injective, then automatically lifts to a faithful representation of the sister algebra. Or in other words, perhaps you have seen this, this algebra of pi and u is exactly the sister correspondent. Would like to see whether there is an analog of this construction for an endomorphism alpha, and it appears there is once you use the machinery of sister correspondences. There are many people have worked with sister correspondence, but here I'm using the work of Katsura, which provided a nice framework that deals with all cases of sister correspondences. In any case, for our example, the Cuntz-Nica-Pimsner algebra is a universal sister algebra generated by a copy of A and an external operator V, and it satisfies this covariance relation. V is an isometry, and also instead of undoing the endomorphism all the time, it somehow undoes it. You have this relation, so some A's are orthogonal to the range of V. Sorry. Yes, to the range of V. But you don't want this for all V's. For all A's, you want them for the annihilator of the kernel. And that is extremely important here. Well, let's see if this indeed generalizes the cross product construction. So if you have an endomorphism, then the annihilator of the kernel is the whole algebra. And in this case, if you take also unital, you see that V is a unitary, and therefore the Cuntz-Nica-Pimsner algebra is exactly what you have, or what you were hoping to have. Things are also good when you start with an injective endomorphism. In this case, you can pass to a direct limit construction. There is an alpha missing here and here. Sorry, there is missing here. You can pass to a direct limit construction through this diagram and have an automorphism between the A infinity and between the infinities called alpha infinity. This is the minimal automorphic extension of the original pair A alpha, and appeared back in the 80s. Peters used it a lot in his work, and then reappeared in Stacy's work when he was trying to generalize this construction. What is interesting, though, is what happens when you do have some things in the kernel. And this ideal here is not that innocent. Actually, it is the largest ideal where the restriction of alpha remains injective. And this is very crucial information. Also, because of this in the covariance relation, V undoes alpha when it applies on this largest ideal where it's injective. I haven't used any representation here for A because A embeds isometrically this Cuntz-Nica-Pimsner algebra. This is also something that you would like to have all the time. The algebra that you construct, the big sister algebra, contains at least an isometric copy of the initial data. And in fact, the Cuntz-Nica-Pimsner algebra is the smallest one that can be generated by A and an isometry that satisfies the covariance relation and has an isometric copy of A. So it's it's not just a generalization for the sake of generalization. It's the smallest thing that we can hope for once we have these restrictions. And of course, also the contribution algebra satisfies the Yates-Varied uniqueness theorem, which is very important for lifting faithful representations to this big system algebra. This is not all yet. More things happen. The algebra that you construct inherits some properties of the original data. For example, Katsura have shown that the contribution algebra is exact if and only if A is exact. And you would like to have something for nuclearity as well. Well, if A is nuclear, then what you construct is nuclear, which makes sense because you just implement some algebraic manipulations here. Unfortunately, the converse doesn't hold. What holds is that this algebra is nuclear if and only if this quotient is nuclear, and the embedding of this annihilator inside the fixed point algebra is nuclear. Katsura has constructed a very nice counterexample where he starts with a non-nuclear A and gets a nuclear contribution. One more reason why this algebra is important it is because it satisfies Arveson's program of the C-star envelope for a specific non-self-adjoint operator algebra. So this contribution algebra, it is the C-star envelope in the sense of Arveson, and I will pause for a second to put some context in this result. So, short intermission for the C-star envelope. We have two kinds of norm-closed operator algebras of subalgebras in B of H. The self-adjoint ones, the C-star algebras, and the non-evolutive ones, so we'll call them NSA. What Arveson noted is that, okay, by definition, every NSA generates a C-star algebra inside the B of H, where H is a Hilbert space, which it acts. However, it may happen that it has the same algebra has two representations that are completely isometric, and the C-star covers the C-star algebras that they are generated there. They are not isomorphic in the strong sense that there isn't any isomorphism that respects the algebras element-wise. An example, the case example in all this in this framework is the disk algebra, the analytic function of the on the disk, continuous on the unit circle, which we know that they can generate isometrically the Toplitz's algebra by sending every the generator Z to the forward shift. But it also generates the continuous function on the closed unit disk, and also generates the continuous functions on the unit circle because of the maximal modulus principle. This bending is always isometric. From all these C-star algebras that you can form, there is one that's minimal, one that accepts star epimorphisms from everything else, and we call this the C-star envelope of AD. This actually works because the unit circle is the Shilov boundary of the disk algebra. So the C-star envelope is a way to generalize the commutative Shilov boundary to the non-commutative context. And Arveson asked whether this holds in general, and the answer is yes, indeed. There exists a representation of A such that for any other representation you take on any other Hilbert space, you can always find a star epimorphism from iota prime to the one that you create here, and this star epimorphism respects the algebra element-wise. And we call this, no surprise that we call this the C-star envelope of A. The non-commutative Shilov boundary will be the kernel of this star epimorphism, and will be an ideal that respects the of A. There are two proofs for this. One by Hamana, where he showed that the C-star envelope can be created inside the injective envelope of A in the category operator algebras, once you apply the toy efforts construction on the injective envelope, and you know a C-star algebraic structure here. Or alternatively, by Christian Machiavelli, you can see the C-star envelope as the C-star algebra generated by maximal dilation. I will come to that a little bit later. What's the maximal dilation? In any case, this affirmative answer here generates the Adamson's program of the C-star envelope, which asks you to, if you are given a non-self-adjoint operator algebra, you're asked to determine and examine the C-star envelope. Now, when we go to dilations, we really like specific kind of dilations. So if you have, for example, just one operator, you don't want any dilation of that, you want power dilations. So dilations that can be written in a lower triangular form, so that every power of t, sorry, every power of u is a dilation of the same power of t, in order to keep the same algebraic form that you have. And the dilation is maximal if it cannot be dilated any further unless you start adding direct copies of other relations. An example that also settles the case of the disk algebra with the unit circle. If t is a contraction, then you can first co-extend it to an isometry and then extend the isometry to a unitary, and you come up with a maximal dilation obtained by unitary u. The idea behind this is you can start forming operators coming from a geometric structure, but when you pass the C-star envelope, you hope that you have more relations, and you hope that you will pass to a better object. That's the hope, and that's what you like to do. So, going back to the single endomorphism on the C-star algebra A, there is a natural non-self-adjoint algebra that you can associate to that, and this is called the semi-cross product of Peters. It is universal with the property that it's generated by a contraction V, and a copy of A that satisfies this covariant relation. So here you also can drop the assumption of the isometry by generating a very big, huge object. It was there is a nice story behind this algebra. It was initiated by Arveson and formally defined by Peters, with the hope that it can encode completely up to outer conjugacy the actions of the dynamical systems. And this is true. If you have it's actually true. So if you have the systems that are outer conjugate, then of course this implies that, or you would hope that it implies that the algebras are geometrically isomorphic. The value here is that this goes back also, well, in many cases, for example, when A is commutative, so when the systems are classical systems, or when alpha is an automorphism, or just injective, or just surjective, and many other cases. This result is of Davison Katsoulis back from 2008, and this is a work that we did with Davison in 2012. The reason why you want to pass the non-self-adjoint operator algebra is because something similar doesn't hold for C-star cross products. C-star cross products, every cross product on A alpha is isomorphic to the cross product of A with alpha inverse. And these two actions may not be conjugated. There is a nice counterexample by Horenberg. Try to convince you here that this non-self-adjoint algebra is something that comes out very naturally you need minimal data to construct it, and also it gives you a lot of information because of this encoding here. Actually, you can dilate contractions in a way to get isometries and still have the same covariance relation. And what Cuntz-Nica-Pimsner showed is that the system envelope of that semi-cross product is the Cuntz-Pimsner algebra. So, these are some arguments why this Cuntz-Pimsner algebra is very, very important when we want to encode dynamical systems by operators. However, it happens that you can see that it has a very nasty algebraic description, and there are some relations here that, well, although you need them, they might prevent you from giving a full detailed examination of this object. So one might ask, why do we have such complexity? And the reason why it comes from the faithful representations of A. So if you have a pair rho and V that satisfies this, in order to prove that the integrated form on the Cuntz-Pimsner algebra is faithful, you would apply some conditional expectation. You will apply the gauge action, you will apply some conditional expectation, and at the end you will come up with equations of this form. So you have some generalized polynomials where I isolated the fixed term here, and it appears that whenever you have this fixed term must live in the annihilator of the kernel. The reason why this happens is because VV star is an identity for this bit, and therefore you can rewrite these equations in this nice form. And as long as rho is faithful on A, you can have that whenever every solution of this equation lives here. So the Cuntz-Pimsner algebra is nothing else by taking by stating that the solutions for these equations are exactly the things that live in the kernel, in the annihilator of the kernel.
V sub n is v to the power n, or what?
Yes, it's v to the power of n. I will go to semigroups shortly, and that is why I use this form. So a question that arises is whether we can connect this Cuntz-Pimsner algebra to a C-star cross product in any case, and come up with a plan that gives us information about this by using whatever we know from the theory of C-star cross products. There is a two-step dilation for that. First, what you want to do is you want to dilate the dynamical system A alpha to an injective system B beta. And the way to do it is, well, you have alpha acting on A. This might have a kernel. So you push out this kernel by considering the quotient map when you take the quotient by the annihilator of the kernel. Now you want this how beta is defined on A, but now you have introduced a new term and you want to keep injectivity. So what you do is you push it a little bit further, and you push this a little bit further, and so on. And this is how you can construct a tail. The idea comes from graphs, actually. So suppose that you have a graph of this form that might have a source, and yeah, this one has a source. Let's also put a sink. A way to get away from having source and sinks is to set up a tail on the sinks. And you can do also this with the source, and you can do the same with the sinks. And therefore, and afterwards you can show that the C-star graph, the graph C-star algebra of this big graph is the same with the C-star algebra of the smaller graph, or the equivalent to that. And whatever analysis you do for graphs that have no sinks or sources applies to all graphs that you can have. So two key ideas here. The one is that we can add a tail. The second one is strong Morita equivalence. Now, as long as you have an injective system, then you can form the direct limit construction, and you can pass from this to the minimal automorphic extension. And the theorem that you can prove in this case is that, okay, on one hand you start with a single endomorphism, you create a Cuntz-Nica-Pimsner algebra. On the other hand, you can dilate it to an automorphic system for which you know the cross product, and you can show that these two are strong Morita equivalent. This is the cunning plan. So whenever you want to find or to prove a theorem in this context, you would like to see whether there is some stability of this dilation, and whether you can prove the same theorem for these cross products, and then push it back. An example comes from classical systems. You can show that the Cuntz-Pimsner algebra is simple if and only if the system is minimal and the group action is injective in this sense. And the reason why is that these properties here are stable under the dilation. So the same thing happens for the automorphic dilation, and from Archibald-Spielberg, you know that whenever this happens, the cross product is simple and simplicity passes between 3 and 4 through strong Morita equivalence. I'm not claiming that you have to do less things. I'm claiming here that the complexity that arises when defining this object can break down in two steps. One step when you check the dilation, and the other step is what happens here at the system cross product context. But hopefully or fortunately, perhaps you have your theorem already at that context, so you can push it. So half of the work might be already done for you. So what you need to check is just this dilation. So the question that arises is whether you can do a similar thing when you have semi-group actions on the system algebra A. So starting from such a system, perhaps you can associate to that a semi-cross product, a non-self-adjoint algebra, find the system envelope of that, on one hand. On the other hand, you would like to dilate this to a group action for which you know the system cross product, and ask whether these two things are strong Morita equivalent. I'm lying a little bit here because I have an A here. There are many ways of associating a non-self-adjoint algebra to a semi-group action, and it's up to you to decide what you want to create first, find the system envelope, and then link it to a system cross product. So there is some flexibility in this plan, and this flexibility allows you to prove some trivial theorems. Or if you are feeling more adventurous, you may want to define something a little bit general here that requires more attention when proving this. Other questions that you can ask is whether the system envelope is some type of Cuntz system algebra, as before. And here I'm just putting the system envelope of a non-self-adjoint algebra. And another question is whether you can describe it simply by star algebraic relations instead of the co-universal property. And then, of course, use this plan to relate properties of the system to C-star properties of this object. With Ken and Adam, we managed to show this scheme for several for general semigroup actions, for several good semigroup actions. So for the free abelian semigroup, or the free semigroup, or whenever you have a spanning cone, or a North semigroup. And this work that we have studies different types, different kinds of dynamical systems that you have there. What was very exciting was the particular case of the free abelian semigroup, which you saw in the next slides. And in this context, we identified what is known as the Cuntz-Nica-Pimsner algebra. And we've moved a little bit forward to study this Cuntz-Pimsner algebra in terms of simplicity. when you have a classical system. There are more properties for system algebras, and in a later work I did similar things for. I checked the stability of the dilation with respect to nuclearity, exactness, and KMS states. In practice, I used this dilation to provide some nice KMS states for the Cuntz-Nica-Pimsner algebra. Right. The reason why this is particularly important is because there has been a lot of work about extending what we know from one direction to multiple directions. For example, how you pass from graphs to higher rank graphs, and put them all in the context of system correspondence and product systems. So even though for system correspondence we know a lot of things, system correspondence is the analog for one direction, we don't know everything about product systems, and we don't know everything, for example, for product systems over Zn plus. And with this work, we managed to use dilations to link the system envelope to the work of Carlsen, Larsen, Simpson, Vitadello on product systems. There are many things in this work, but I chose a specific thing that has to do with dilating. And so, for example, what I want to show you is how you dilate systems over Z plus n, with this constraint that I want to have some word equivalence between the operator algebras. So I will write this I to denote the generators of Z plus n, and a dynamical system of Z plus n is defined by n commuting actions. It's not nuclear physics here. The requirements that we have to build first algebra, first operators is, well, we want n contractions VI that satisfy the covariance relation, well, because we want to mimic what we know for Z plus. And we also want that V to be a semi-group representation of Z plus n. So we want these VIs to commute. However, this may not be enough. If the aim is to reach a cross product, then when you want to apply it for trivial systems, so when A is C and everything is the identity, then you would like to dilate the VIs to unitaries. You would like to be able to dilate n commuting contractions to n commuting unitaries, and that doesn't happen all the time. Parrot's counterexample shows that this fails for n equals 3 and more. So instead, you want to find things that actually dilate, and this is a big subject in dilation theory. What type of contractions, of commuting contractions, dilate to unitaries? In our case, we focused on double commuting contractions. This means that the VIs and the VJ stars commute as well. The NSA that we constructed is the Nica covariant, what we like to call the Nica covariant semi-cross product, generated by monomials, let's say generalized monomials on the VSs, or as in the semigroup, and double commuting contractions, and that's it. One may ask whether this is void, or whether there is actually at least one representation, and there is one coming from the left regular representation for semigroups. And it's here where you see why you want double commuting. So for every I, you form SI to be just a shift at the ith direction, and for any A, you form pi to be the orbit of A along the diagonal. The reason why we call it Nica covariant is because we can dilate such pairs to double commuting isometries VIs. And there is some nice work about double commuting isometries by Nica. They form a specific type of representation. So this is where the Nica covariant comes from.
Sorry, could you just, I didn't manage to catch what doubly commuting meant.
Yes, doubling is
beautiful.
You you have that the VI is the VJ's commute, but also you have that the VI the VJ star commute whenever I is not 0. Now, by using this information and because the VIs are isometries, I understand that the system algebra must satisfy at least these relations. So whenever it is generated by an A and some V's, then I can write the system envelope in this nice form as a nice linear space. This doesn't tell me more things about the V's and about extra relations here that the system envelope may satisfy, but still it gives me some nice way out, because now I can apply things like gauge action and I can take conditional expectations to that, and I can find a nice form for its fixed point algebra here. Well, reductions. The plan is to dilate the system to a group action over Zn, and if you are very lucky and everything is injective, then you do nothing else but creating the minimal automorphic extension of that simply by using the partial order in Z plus n, or this is just immediate. So for every I you construct these alpha i's that come from this commuting diagram. In this case, the system envelope is nothing else but the nice cross product that you have of b by beta, and this is pretty much straightforward. So the actual plan, or the revised plan, is to manage to dilate a system that might have some things that have a kernel to an injective system, meaning that everything is injective. And again, remember what happens in the n equals 1 case. What you do is you take alpha to act on your algebra along with a shift to the quotient with the annihilator of the kernel, and then you shift everything forward. The reason why this is injective is because if something was in the kernel of alpha and in the ideal, it will be the annihilator of the ideal, and so it had to be 0. And beta, of course, is injective here because it just pushes everything by 1 coordinate. What I've prepared for today is, well, not actually do it for every n, but show you how it can be done for n equals 2. And then stick all the details in one very dense slide and ask you to believe me that it holds for every n. So I have two commuting endomorphisms. The plan is to construct two injective commuting endomorphisms that dilate the alphas. If you would like to mimic this, then instead of having just the annihilator of one kernel, you would take the annihilator of the two kernels, okay? And you name this as I. For things that will come clear in a couple of seconds, you name I1 to be the maximal ideal in there that remains invariant under alpha 2, and you do the symmetrical for I2. So you go and you define beta 1 by the solid arrows and the b2 by the broken arrows. On A, you have alpha 1 and alpha 2. You want to push out the kernels on its side, and you do it by using the quotient maps on I1 and I2. Now you go here, and you have to define an action that goes up and an action that goes to the right. And the target here would be the quotient by the entire ideal I, and you can define beta 2 by applying one element by alpha 2 dot and pushing it a little bit out by this quotient map. This is why you want I1 to be invariant under alpha 2. And in order to keep now injectivity here, you just push everything to the right. You do the symmetrical thing in the other direction, And so you have defined everything in this in the axis and in this one point. So what's left is to define everything here, where you just push everything out by the identity. So along the here you put A, along this axis you put just one quotient which remains the same. You put another quotient here and a third here that remains the same everywhere. Now it is immediate, almost immediate to check that beta 1 and beta 2 are both injective and commute. However, this construction will fail. And I'm bringing this up because it was our first attempt. The reason why it fails is because we want this restriction, we want the operator algebras that we construct to satisfy a nice strong Morita equivalence. And this system here, this dilation doesn't help. Actually, if you didn't have this restriction on the strong Morita equivalence, you don't need to do something that scientific. Put every ideal here to be 0 and just keep the same diagram by putting identities. You construct something that is injective and you're done. But the whole point is to find exactly which ideals you have to put here in order to keep the strong Morita equivalence. So this requirement that we have strong Morita equivalence is very strong. To see why this construction fails, first let me tell you how we ended up with this ideal. Well, if you have faithful representation of a doubly commuting system of isometries, then you apply the gauge action and some conditional expectation, and when you want to see whether the integrated representation on the system envelope will be faithful, you end up with this type of nice equations. Okay. Again, I isolated the fixed term by using the fact that these projections act as an identity here. You can transform this equation into this nice bit, from which you take that the fixed term must be orthogonal to both kernels. However, this is not the only type of equation that you may end up with. You may end up with equations that are supported just on one direction. And in this case, you may be a little bit more strict and use this projection as an identity for this bit, and use this to transform these equations into this nice form, depending only on the fixed term, which shows you that the fixed term is orthogonal to the kernel of alpha 1. You can also check from that, and because the VIs are double commuting, that alpha 2 and every power alpha 2 on this element will still be orthogonal to the kernel. And this happens because alpha 2 is implemented by V2 star. So you can go here and apply on both sides, on one side V2 star and on the other side V2. They commute, they will come in, and they will produce alpha 2. So instead of using this previous I1, I told you, you have to transform this a little bit. You have to, instead of taking the same I, you have to take the orthogonal, the annihilator of the kernel over the first action, and this you name as I1. And you do the same thing, the symmetrical thing for I2. You go back, you cross your fingers, and you hope that everything works by just rearranging, by just substituting the correct ideals here at I1 and I2. Well, of course, this generalizes then equals one case. However, the difficulty now is to show that these betas commute. Okay, that's not very, very difficult. But also to show that these betas are injected. And the problem comes here, to show that things are injected. So to show that beta 2 is injected. It is true, it's not immediate, and it is one of the technical things that we really have to prove in this paper. So, to wrap everything up, you can, this is the dense slide that I hope, I'll step in, I will move my hands, don't look at it, it's pretty ugly, it's pretty dense. But the whole point is that this construction, if you understand the construction for n equals 2, then you can extend it in more directions. And at some point you have to use what happens for the support and what is orthogonal to the elements of Z plus n. That's it. If you write it in a neat way, then everything works perfect. So how the plan is fulfilled for this type of semi-group actions? First, when you're giving a semi-group action over Z plus n, first dilate it to this injective system by adding this multi-dimensional tail, and then for this injective system apply the automorphic extension. Then you can show that the C-star envelope of the nickel covariance semi-cross product is Morita equivalent to a cross product. So, but by using this, you can come up and start saying many things about the C-star envelope once you have some stability of dilation and you use the correct theorems from the C-star cross products. However, one thing that we should keep in mind though is that the C-star envelope is defined by a co-universal property, and the only thing that I told you, that the only thing that we know up to this point is that if it is generated by A and V, then it can be written as this nice linear span. But we don't know more things. Actually, this was the challenging point in the proof, and we were able to show this entire thing without knowing what algebraic relations determine the C-star envelope, just by using co-universal property. So at the end, we start thinking, okay, what can we say more about the structure of this? Is it also universal C-star algebra with respect to some C-star algebraic relations? And it appears that yes, it is. So for the n equals 2 case, we arrived at a bunch of equalities that we need to solve when we want to see whether a representation of A leads to a faithful representation of the entire thing. And we use the solutions ideals of these equations to produce the tail. This appears to be more than just a coincidence. And in fact, the Cuntz-Nica-Pimsner algebra, you can define the Cuntz-Nica-Pimsner algebra to be universal with respect to this property. So it is a universal object generated by double commuting isometries, satisfy the covariance relation, and they satisfy also a bunch of relations based on the solutions ideals. Practically what this says is that this equation must hold exactly for the solution ideals, nothing more. If we pass to, if it's satisfied by more things, then we lose the algebra A of the dynamic system. And the theorem is that this Cuntz-Nica-Pimsner algebra, which we denote by NO, is the C-star envelope of the semi-cross product. So you can rewrite everything now in the C-star algebra, in the C-star algebraic context. So you can use this dilation now, not referring to any C-star envelope, and say, okay, I now know exactly what is the Cuntz-Nica-Pimsner algebra I'm looking for, and I can relate it by strong Morita equivalence to a nice cross product. Again, the good thing is that this algebra satisfies the Gauss-invariant theorem with respect to this type of representations, and this is exactly why it is the smallest C-star algebra that satisfies these algebraic relations and contains still an isometric copy of A. It's the smallest thing that you can generate from the dynamical system. You can use this as an application. You can use this, for example, to classical systems, and find exactly when the Nica-Pimsner algebra is simple, and this happens if and only if the system is minimal. This means that it doesn't contain invariant ideals under the action, and it is topological free in the semi-group sense. And this happens because the dilation, these properties remain and they are stable under this dilation. And again, by Asmus-Pilbert, these properties for automorphic systems or homeomorphic systems are equivalent to having simplicity of the cross product. And they use strong word equivalence as before. You can move on and you start asking what happens with exactness. It appears that exactness still is stable under this dilation. And you can use also this dilation for nuclearity. You can show that the Cuntz-Nica-Pimsner algebra is nuclear exactly when these embeddings in the minimal, in the direct limit are nuclear. Again, the same pattern. The embeddings will give you that this direct limit is nuclear. This is the only thing that you need to prove that the cross product is nuclear. Actually, for nuclearity, you can show that if A is nuclear or if A embeds in at least one fiber in a nuclear way, then the Cuntz-Nica-Pimsner algebra is nuclear. Of course, the converse is not true, and you can take the same counterexample of Katsura, just extend it to more directions by adding identities. Some final remarks. There is also another variant which is called the Nica-Toplitz, and it's generated by the left regular representation of the, it's generated by the Fock representation of the system. And for this, you can show that nuclearity and exactness are equivalent, nuclearity exactness of A are equivalent to nuclearity and exactness of this Toplitz algebra. And again, you can go and you can start and you can use the scheme of Lacan-Rayburn and check the KMS states of both this sister algebra and the Kuntz and its Kuntz type.
But what do they tell you, like these KMS states, like for the algebra?
You can use them as an invariant. So,
but we're like to distinguish them, or like invariant for what?
invariant for isomorphism of specific isomorphisms of algebras.
Okay.
The specific isomorphisms have to respect the action of the real numbers. But this appears to be there are some open questions for non-subfactorial algebras which you can lift to isomorphic questions about the sister algebras they generate. And because you ask for for a specific form of isomorphism at the NSA level, the induced isomorphism must respect the gauge actions. So in another work, I try to use the KMS states to disprove a conjecture, but I managed to prove more to give more arguments that might be true. Other things that you can do, you can start extending. You can look for simplicity of the Cuntz-Nica-Pimsner algebras by using the work of Callender and Kennedy. Well, of course you have transformed everything into semigroup actions, and you have from the semigroup context to semigroup actions of our sister algebras. And this is something that we wish to do in the future. And finally, the techniques that we use here for both Toplitz-Nica-Pimsner algebras and Cuntz-Nica-Pimsner algebras, especially for the Kuntz type, I'm pretty confident that can be used to show what's the Kuntz type for a general product system, and not just for this example of product systems. And I will finish here with the list of references. Questions or comments?
Is there any work on one parameter?
Well, there is the Z plus, but you may want to.
No, I mean continuous.
Continuous, yes, that's. There aren't too many things that have been done. there is a variant of a semi-cross of a cross product in a non-subfactorial context that also incorporates locally compact groups, but for locally compact semi-groups, no, I'm aware of. It's very convenient to use a discrete semi-group. I'm honest here. Okay, it's much more easier to write everything as a sum instead of an integer, and it's much easier to check things. But I'm sure that things can be done there. Indeed, there is a work for dilating one parameter, let's say semi-group representations, and these are always the base point for moving to semi-group actions, as a case example for trivial dynamical systems, and perhaps these ideas can be extended to semi-group actions. Yeah, but it would be very interesting to see a continuous handling of these results. So for one thing, I don't know how you can construct a tail for that. The tail that I gave you is on the grid of the semi-group, right? Z cluster. And you might want something, a continuous version of that.
Further questions or comments, and let's thank the speaker again.